All right, hi everybody. I am doing this recording to kind of help you with the calculations for the Hess's Law Lab. I have my own data listed here, so you probably have different sets of data than I have, but the work will still be exactly the same. So remember the whole idea with the lab, you had two reactions and we're trying to figure out how much heat was released. Both of those reactions made the temperature increase. So we want to figure out how much heat was released. So again, to use that graph that we used, the reactants were higher than after we reached that activation energy. The reactants were higher than the products. So we have this loss of energy, and we sense that as heat, and that's why the temperature increased. So in order to calculate that, we're going to have to do it backwards. We're going to calculate how much heat was gained by the hydrochloric acid within that calorimeter. So we're going to do that first, and then we're going to do the sort of the inverse, that's not quite the right word, of it to calculate what the actual heat given off was. So to calculate how much heat was gained during the calorimeter part, we're going to use the Q equals MCAT, the Q equals MC delta T. And remember that C is the specific heat. So Q is what we're looking for. So we're going to write Q. M is the mass of, and in this case, we're going to pretend it's water. It's really hydrochloric acid. The mass of water is super cool because 1 milliliter of water equals 1 gram of water. That's how the metric system is set up. That's not 100% true for hydrochloric acid, but our hydrochloric acid was really dilute, so it was mostly water. So we're going to say, okay, close enough. So if we have 100 grams of HCl, we're going to say it's like 100 grams of water, or 100 milliliters of water. So we're going to go ahead and put 100 grams right there. So everybody should have right around that number. C is going to be the specific heat of water. We should use the specific heat of hydrochloric acid, but it's so similar to just water that we can get away with using the specific heat of water. So everybody would write the specific heat of water, which is 4.184. And it's got a wacky set of units, joules per gram times degrees Celsius. And you'll see that all the units will cancel out and we'll be left with joules when we're done. So right now you can see that the grams have canceled out. We need degrees Celsius to go away so that we're left with joules. So now we need to do the temperature change. And this is where you're probably going to be different than mine. So my temperature change, I'm just going to add it up really quickly. So the difference between my final temp and my original temp, give me just a second to do that. I'm not going to say the numbers so that you could be doing it independently. And now I've got my temperature change written down. So now go ahead and do the math and figure out what Q is. So multiply those numbers together. And what you have calculated is in joules. Oops, that looks like a G, not a Q. There we go. So this was mine, 4309. Oops, actually, not cool. Oh, what am I doing? Mine was, if I use sig figs, mine was 4310 joules. And when we're doing delta H, we usually want it in kilojoules. So I'm going to go ahead and convert that into kilojoules right now by moving the decimal over 3 places. So mine is 4.310 kilojoules. That's what Q was. So that's how much heat was received into the calorimeter. So we say that that's super similar to the heat that was given off by the reaction itself. And that's what we're trying to calculate. So the heat that was given off by the reaction is the negative version of what we have there. So we would say negative 4.310 kilojoules of heat were released by the reaction. So let's we're almost ready for that step, but not quite yet. What we need to do now is to take a look at the mass of the MgO. So you need to convert that into moles so that we can do kilojoules per mole. That's what delta H is always measured in. It's not some random number like 1.22 grams. It's got to be per mole. So write down your mass. So my mass was 1.22. And then, as we always do with the mole roadmap, or however, draw your line. What unit do you want on the bottom? You want grams on the bottom of, and this was the MgO, and you always put 1 mole of MgO on the top. And so what is the grams of MgO? We find it on the periodic table. Give me just a second. So magnesium is 24.312. And oxygen, obviously, you probably have that one memorized, 15.999. So you can write it down with me. 40.311 is the mass of magnesium oxide. So now our grams cancel out and we're left with moles of magnesium oxide. So now I need to do the mass times 1, I don't care if you do the times 1, divided by the molar mass, 40.311. And for me, the number of moles is probably a little bit higher than the moles you had, because we weren't close to 1 like you guys were. Mine is 0.0303, and that's in moles. So that's my 3 sig figs right there. So now I've got kilojoules right here, and I've got moles right here, so we're going to combine them. So I'm going to make the kilojoules negative, remember, so negative 4.31 kilojoules for every 0.0303 moles were given off by that reaction. So now go ahead and enter that into your calculator and make sure that you give it a minus sign. So 4. I'll try not to talk too loud because I know you're doing different math than I am. Okay, so for me, I got that delta H was negative 142 kilojoules per mole. I've got a couple students in the room. Did you guys get close to that? 172. That's a lot higher than mine. What did you get for your Q? 2.510. Okay, that's fine. That's fine. Your numbers are just going to be a little bit different than mine. So, and we definitely have error. Remember, one of the biggest errors in this lab is the fact that we have these calorimeters that are not closed, so heat is escaping up through the top. So, not a huge deal. What I just realized, unfortunately, is that I wanted this as workspace for my next equation, and I didn't give myself any workspace. So I'm going to try to. I didn't give myself enough workspace. Okay, so hold on just a second. I'm going to delete something here. So hopefully you all wrote that down, what you need to write down, and I'm going to go ahead and erase this so that I have some workspace. Or maybe I could move it. That's what I'll do. I'm going to move it. I'm going to move this to a new location. Computers are so handy, aren't they? Look at that. I love it. Okay, I'm such a nerd this way. Okay, let's switch up colors so that we can see it differentiated a little bit more clearly. So now we're pretty much going to do exactly the same thing with reaction 2. We need to find out what the delta H was for reaction 2. It also got warmer. It gave off heat, so the calorimeter is accepting some of that heat, and the reaction is going from a higher energy level to a lower energy level. So we know that the delta H is going to be the negative of the heat that was gained by the calorimeter. So we're going to do the same equation. Q equals, oops, I'm not in writing mode. Q equals MC delta T. So Q equals, and now my mass again was 100, and yours should have been right around that. We're going to, again, because we're using hydrochloric acid, we're going to assume that it's like water. So 4.184. It's hard to talk and do these at the same time. 4.184 joules per gram times degrees Celsius. And then your temperature change. And I'm going to go ahead and do my temperature change here. So go ahead and figure out what your temperature change is. And then go ahead and multiply it out so that you get Q. I'm going to give it 3 sig figs because this was 3 sig figs. Oops. And my first answer is in joules. And so I'm going to convert that answer to kilojoules. Ooh, I just made that 4 sig figs by adding that 0. That was my bad. I shouldn't have added that extra 0. I bet I did that up at the top too, didn't I? Make that last 0 go away. Now it's 3 sig figs. Okay, so kilojoules. There we go. Okay, so now what we want to do is figure out how many kilojoules per mole, and we're going to add that minus sign to this answer right here. We're going to add a minus sign to that. So I'm going to start with the mass of magnesium. So I'm going to write down the mass of my magnesium, which will be different than yours. My mass was 0.26. I think most of you had a mass right around 0.2, somewhere in that ballpark. What did you guys have for your mass of the magnesium? 0.21. Okay, so mine's a little bit bigger maybe than some of the masses that you guys had. So that's mass of magnesium, and as we always do, 1 mole of magnesium over the grams of magnesium from the periodic table, and that's 24.312. So everybody does that number the same. 24.312 is what goes on the bottom of your conversion factor. So conveniently, that made grams of magnesium go away, and we've converted it now into moles of magnesium. Question? 24. Can you guys not read my sloppy handwriting? What's that? I know, 24.312. Okay, so do the calculation, figure out how many moles you had. And I'm going to write mine down here. And go ahead and put it in with 3 sig figs. And so that's my moles. So now I'm going to take the negative of what was in the calorimeter and put that with my moles. So mine is going to be negative 4.48 kilojoules. Oops, I shouldn't talk out loud because I know you're trying to work and you have a different number. Over, and then the number of moles that you had, and you're going to go ahead and divide that. Get my picture out of the way. Maybe I'll scooch it over here. There. Okay. And this is going to be our delta H that we're going to have for reaction number 2. I feel like that's a really small number. What did you guys get? What did you get?
I still did the last one. Oh, wait.
Am I doing it right? I hope I'm doing it right. Give me a second to go back and look, everybody. I just want to make sure I'm not screwing something up. I was screwing something up, so I typed it in incorrectly. So now I have the right answer. I'm glad I redid my math. So I got a negative 419. So negative 419 kilojoules per mole. And so that's for that's delta H of the second reaction. That's delta H of the second reaction. Should I pause, you guys? Are you keeping up okay, or should I pause? You're good? Okay. Okay, so now let's take the 2 answers, the 2 delta H's that we just got, and let's put those on the equations. So if you scroll back up to the top of your lab, I'm going to scroll down because I wrote them down here. So here are the 3 equations. This is equation 1, 2, and then 3. Equation number 3, they already gave you the delta H value for. So let's write in our new delta H values, and your delta H values are going to be different than mine. So I'm copying them from on my paper. You copy them from your paper. And my other one was... Okay. So now we know the delta H's for all three reactions, and we're trying to get to this target reaction right here. So this is where Hess's law comes in. So we need to rearrange the three equations so that we get to our target reaction. So I'm going to just kind of eyeball it here for a second. What I see right now is that MgO is a product, but in reaction number one, MgO is a reactant. So my gut tells me let's reverse it. So I'm going to go ahead and write flip on this one. So if I reverse this entire equation, what does that do? Well, let's just go with that for the moment. So I flip it. It means that my product is in the right place now. I have a 2HCl right here. That is now a product. If I look at equation 2HCl is a reactant, so they would cancel out right now. So I think I'm going to go with this. So I'm going to cancel out 2HCl. Let's just see if it works. We can always reverse if we need to. Okay, now if I have reversed this equation one, MgCl2 is now a reactant if it's backwards. And in equation two, MgCl2 is a product. So they would cancel each other out. I'm liking it so far. Okay, and now the last one, water is in this equation now that I've flipped it, water is a reactant. And look at equation three. Oh, I love it. In equation three, water is a product. So they would cancel each other out. Is there any more canceling that I need to do? Let's see. What'd you say? The hydrogens. Thank you. Okay, so this hydrogen right here is a product. This hydrogen right here is a reactant. So they cancel each other out. That was about the easiest Hess's law we've ever had. We didn't have to multiply or do anything. So what we're left with, this is a product and it's the right number. There's no special coefficient or anything like that. There's Mg as a reactant and there's 1/2 O2 as a reactant. So we are done. So now, because we flipped equation one, for the folks in the room, what do we need to do to our delta H because we flipped it? Make it a positive. So I don't know how to do that so you're really clear, but just turn your minus sign into a big plus sign. So it changed because somebody's coming to the door, so I might need to pause it. Can you guys let them in and see who it is? Give us just a second here. Hi, Amelia. I'm in the middle of recording a video, so we're going how to solve the lab, so I'll be done in just a second. Okay, so now we've got our numbers, so now we just need to add up our numbers. Remember that the purpose of this lab was to figure out the delta H for that target reaction. So all we need to do now is add up these three numbers, and that gives us our delta H for the target reaction. Yours is going to be different than mine, and that's not a problem. So let me add mine up and you add yours up. And don't forget to use your negatives because that's going to make a big difference if you forget that. Where's my negative sign? Ah, there it is. And I got a negative 562.8. So delta H of the new reaction is negative 562.8, and that would be kilojoules per mole. What did you guys in the room get? 584? You're even closer to the right answer. And you guys did the same lab?
Yeah, I just did like different numbers.
Okay, so something's a little bit different on theirs, but I will tell you what the right answer is. KJ, how do we know what the right answer is? This is where you go to your table of thermodynamic values, and I had it, and now I don't know where I put it. Where did I put our table? Does anybody have their table handy? You have one? Okay, let me just look at it really quickly. So we're going to look up, and I mentioned this in class, but for the target equation, Mg is an element. So on your thermodynamic table, it's a 0. Oxygen is an element. So it's also a 0. So the only one that we need to look up is magnesium oxide, and MgO is a negative 601.6 kilojoules per mole. So this is the right answer. This is the standard answer that's been calculated by scientists in perfect laboratories, not like our styrofoam cup laboratories. Okay, so, and remember that when we're calculating this, the real way to calculate that is to do products minus reactants. So our product was minus 601.6 minus, and the reactants is 0. So that's why our delta H is negative 601.6. That's what we're supposed to get. So now you just need to calculate your percent error. So how far off were you from the correct answer? And then the last thing, and I'm just going to end the video here, the last thing you need to do is just to mention why you would be off from the correct answer. So what were things, and things that you could say: the calorimeter is not a perfect calorimeter, heat escapes out the top. We were using hydrochloric acid instead of water. So like our specific heat wasn't exactly right, and the mass isn't exactly right. It's pretty darn close, but it's not perfect. And so that would be sources of error. And then there's always your own personal error. How careful were you in measuring the 100 milliliters of HCl? How careful were you in reading your thermometer? Are you sure that was the highest temperature? Those are all things that go into error that gets added in here. So, okay, ladies and gentlemen, I'm going to go ahead and stop. That should be enough for you to be able to finish this lab. Have a great day.